Hello everyone. Today my colleague Mani and I will introduce network entitlement, which is meta solution for service traffic isolation. Here is the agenda for today. We will first go over the motivations for the system, then we will describe how the entitlement is negotiated and approved. Then we will introduce the large-scale distributed system that enforces the entitlement. At Meta, we categorize our network traffic into different classes of service. The most premium class is reserved for control plane services such as configuration distributions. The least premium class is reserved for heavy and bulk data transfers. For different classes, network offers different levels of failure protection guarantees and SLOs. For example, we may offer a 4.9 availability SLO for the most premium class, but we may only offer a 2.9 SLO for the least premium class. The same class of service definition is used consistently in our planning and operational systems in all layers of the network. From our operational experiences, there are a couple related problems that can benefit from a common solution. First, our network traffic is growing at a very fast rate. While we're constantly trying to deploy new capacity to keep up with the demand, but a better resource management solution is still necessary. Second is service isolation. In production network, traffic patterns of services are often unpredictable due to new feature rollouts or bugs. In those situations, a class of service is often not sufficient to provide isolation across services, since one service may affect others in the same or lower classes. This highlights the need for a better service resource isolation solution. And the third reason is that since we're offering the network as a service to our internal users, we would like to be held accountable for the quality of network we deliver. And that means establishing a clear contract with SLO expectations. Network entitlement is our solution to those challenges. For the rest of the talk, we will focus on the entitlement solution on the bad area network, which is also the most challenging due to its non-uniform network topology and traffic pattern. Network entitlement is our solution to those challenges. It is a bandwidth contract negotiated between network and the few services that have a major footprint on the network. Network entitlement is work conserving, which means if the services does not go above their entitlement, their traffic performance will be guaranteed with a predefined SLO. However, if the services go above their entitlement, the overflowing portion's performance will not be guaranteed, but they will still be transmitted with best effort. The categorization between conforming and non-conforming traffic is achieved with DSCP marking with the help of our runtime enforcement system, which we will introduce later. Network entitlement uses the host model as the basic abstraction level to express the demand contracts, and we will go over the host model next. In traditional traffic engineering problems, network traffic is often formulated as a set of pipes, where both the source and the destination are specified. However, in the host model, the traffic is specified with a set of hosts, where either the source or the destination is specified, but not both. When only the source is specified, the implicit assumption is that the destination may go to any of the other regions. And similarly, when only the destination is specified, the source may come from any other region. In other words, the host model specifies the total ingress and egress capacity of a region, and it means the host demand is the generalization of the pipe demand. So using host as a foundation gives us a few advantages over the traditional pipe model. First, we hope to make the system as simple as possible. If we have n regions, then using the pipe model will require O of n squared different entitlement contracts. However, under the host model, we only need order of n different contracts, which massively simplifies our negotiation. The second reason is the efficiency. The pipe model is often inefficient due to sum of peak issues, where the sum of individual flow peaks will exceed the total peak of the overall traffic, which causes the demand inflation. By switching to host model, we have observed as much as a quarter reduction in total demand. and it in turn means higher entitlement efficiency. The third motivation is the flexibility. The whole specification can absorb many common demand shift patterns without having the need to renegotiate the entitlement, which also means lower maintenance burden. And lastly, the host model enables our users to treat the network as a resource, just like compute and power. They can simply refer to the total egress or ingress of a region without having to specify the remote end. Here is how the entitlement contract is negotiated. We start with the forecasted network demand in the host format. Then the entitlement approval engine takes the demand and network topology as input and produces entitlement approvals. In case where not all the requests can be approved, we may work with services to explore alternative options such as demand shift or demand reduction. After service review, the entitlement becomes official and we hand it over to the runtime enforcement system. In order to get an accurate demand forecast, we use a tree-based regression model that takes the historical demand as input and also power, and uses planned future power for prediction. And services will have an opportunity to provide additional insight, such as upcoming architecture change, which have the potential to change the traffic pattern significantly. While the network entitlement provides an abstraction level to our users, internally we still need to translate the host model into pipes to do the approvals. On a very high level, we translate the host demand into a set of representative pipe matrices. The algorithm guarantees that if we can accommodate each one of the pipe traffic matrix, we have a high confidence that we will be able to accommodate the entire host. For each one of the pipe traffic matrix, we additionally use the network topology and fiber reliability as input to calculate how much approvals we can make based on the SLO requirement. To be conservative, the final approval is determined by the minimum approval across all the traffic matrices. We have a few publications that go over the details of the algorithm, so if you're interested, feel free to check those out. There are a couple techniques we use to further improve the efficiency of the algorithm. The first one is the host segmentation technique. While the host model is extremely flexible, it can sometimes be too conservative and allow for traffic patterns that we know will never occur in real life due to service architecture constraints. And in those situations, we know that if we can specify some additional locality constraints to the open-ended host direction, then we will be able to reduce the problem space significantly, and which in turn means higher entitlement grants. The second technique stems from how we model network demand. The service's network entitlement is often set to a value that is very close to their peak, but we know that different services doesn't necessarily peak at the same time, which is another sum of peak issue that causes demand inflation. We have algorithms that take those into effect and model the demand inflation, provide adjustments accordingly. The third technique stems from the fact that the network follows a strong daily pattern, where the traffic often peaks at 7 a.m. Western time and drop off after that. We also have algorithms that can take the demand drop into consideration and use it to our advantage to make additional approvals in the off-peak hours. Now that we learned how the network entitlement is approved and negotiated, it's time to turn our attention to the other core piece of the solution, which is the runtime enforcement system. And Mani will go over that next.
Thank you, Guanqing. I'm Mani, and for the rest of the talk, we'll focus on how we enforce the entitlements in production. The entitlement problem statement can be seen in two parts. The first part is all traffic within the granted entitlements, that is, the conforming traffic of the services, should get the promised SLO guarantees. And the second part is any traffic beyond the granted entitlements, that is, the non conforming traffic of the services, should get deprioritized. In other words, it should not compete with the conforming traffic in the network. Let's take an example. Let's say there are like 5 services in the network, and all of them have been granted entitlements. And let's say 4 of them are using the network within the entitlement grant. But the fifth one exceeds its grant, that is, it has some non conforming traffic. We want to make sure that the non conforming traffic of the fifth service does not compete with the conforming traffic of any of the five services. And as long as we do this, the first claim gets fulfilled by itself because the way we have granted entitlements is such that if all services have their traffic within the granted entitlements, then they should get the promised SLO. Now, how do we take care of this non conforming traffic? Do we drop them completely or do we remark them into a lower QoS class? At Meta, we have experimented with both these approaches. Remarking, of course, has been operationally way more simpler. Also, it gives us a more efficient usage of the network. Now that we know we are remarking, how do we actually go about doing it? Do we use host or the network? At Meta, we use a combination of this. So the hosts have the responsibility of identifying and classifying the non-conforming traffic, and the network takes care of ensuring the non-conforming traffic gets the lowest priority. It does this by setting up queues for the non-conforming traffic, which has the lowest priority in the network. And each service typically spans like large number of servers. How do we make sure the servers collectively make a decision on what is non-conforming traffic? We can try a centralized approach or a distributed approach. At Meta, we use a distributed approach where each server makes this decision locally, but the decision is consistent across all the servers which run the service. Now that you have seen how we do the remarking, what granularity should we pick? Should it be per packet? That is, we run this decision per packet within each flow. With TCP, this can be problematic because the non-conforming and conforming traffic could take different paths, could have different latencies, and this could cause reordering for the service and really affect the service. So it's really an option between per flow and per server. In this, of course, per flow by design is way more accurate. But at Meta, the services for which we grant out entitlements is like so large that each one of them runs on thousands of servers. So even if we do per server based granularity for remarking, we get accurate results. Now, this is how the entire solution looks like. We have a control plane which is distributed. We do the actual remarking on the servers using BPF, and all of this is driven by policies. The entitlement policies could look something like service X gets this much entitlement in this region in this QoS class. This is how it looks like within a host. Let's say the application is sending some bytes, it gets to the BPF program. The BPF program has two inputs. One is the set of entitlement policies, and the second one is aggregated counters. These counters tell the BPF program the total usage of the service across the many servers on which the service is running. The BPF program takes both these inputs and then makes a call on like what should be marked as non-conforming. Let's say if the total usage of the service is twice that of the granted entitlement. In this case, the BPF program should ensure that enough number of servers mark the traffic as non-conforming so that 50% of the total traffic of the service ends up as non-conforming. And the whole picture looks something like this, where let's say there are two services, service A and service B, and two QoS classes, class X and class Y. Both class X and class Y have different queues in the network devices. Now let's say service B is exceeding its entitlement in class Y. In that case, the hosts running service B remark the excess traffic as non-conforming. The non-conforming packets get to the network devices. The network devices have a different queue for the non-conforming traffic, which has a lower priority than the other class of service. This is a snapshot from production spanning over 10 days. The green portion is conforming traffic and the orange portion is non-conforming traffic. This shows that for a service which spans like many thousands of servers, we have been able to accurately mark any traffic which has exceeded the entitlement as non-conforming traffic. How do we make sure this massive system runs as expected in the network? It's not a surprise to services. For this, we run periodic large scale tests. We take a region, take a big service, reduce its entitlement so that some of its traffic ends up in the non conforming bucket. We also sometimes introduce congestion in the network so that the non conforming traffic gets squished, maybe get dropped. So this gives the service a taste of what happens if the service exceeds its entitlement. Now, the key takeaways from this whole program. Typically, when a service sends a large amount of traffic into the network, it has to worry about what other services are sending traffic into the network. Where is the service sending the traffic to? But with network entitlement, the service just needs to worry about whether the amount of traffic it is sending is within the entitled amount. And the network art makes sure that if the service is sending within the entitled amount, it gets a promised SLO. So there's like a clear accountability. And also, it gives isolation. As long as the service is within its entitled amount, it's protected from all other misbehaving services in the network. And throughout the process, from the design to the implementation of this program, we have made sure the constructs are simpler, like the host model, or choosing remarking instead of dropping the packets, or remarking at the granularity of servers. All of this has helped us to scale and keep it operationally simple. At this point, we basically run this on the entire fleet of meta servers. And the last point is testing. We periodically do very large scale tests, extensive tests to make sure none of this is a surprise to the services. We have more details about this whole project in a couple of places. One is a blog post about network hosts. We have a SICOM 2021 paper on hosts, which goes really deep into the host modeling. And this year, we have a new paper on entitlements, which goes into the implementation aspects of how we have done this in production. And this goes into the details of the entitlement algorithm as well. Thank you. Thank you for this opportunity.